Hello, my name is Wahid, and I want to talk a little about my work on developing automatically polyconvex strain energy functions with neural ODEs. This is a work in collaboration with Professors Tepole and Sally Costabal. Before I begin, here is a quick overview of what I will be talking about today. I will start with an introduction to constitutive material modeling. Then I will talk about polyconvexity, neural ODEs and how we use them. I will showcase the performance of our model. Finally, I will show how we apply the model in a finite element environment and conclude my talk. The current standard in the modeling of biological tissues is the use of expert-constructed, closed-form material models. But these models often require expert knowledge to use, and they seriously lack flexibility. To overcome these shortcomings, many researchers have been focusing on data-driven material models in recent years. Like all material models, these have to obey some physical constraints, such as polyconvexity. But in most studies, polyconvexity is ignored, replaced by simpler criteria, or at best, some form of convexity is imposed in an approximate way using specially designed loss functions that penalize deviations from convexity. But this is problematic due to many reasons, and there is no guarantee that the resulting strain energy function will be polyconvex anyways. So the question is, can we guarantee polyconvexity in a data-driven framework? So what is polyconvexity? A strain energy function is said to be polyconvex if it is a convex function of the deformation gradient f, cofactors of f, and determinant of f. One subset of such functions involves the sum of three components, each of which is a function of one of the arguments. But working with these tensorial quantities can break the principle of objectivity. So we opt to work with the invariants of deformation instead. These invariants are in turn functions of f, cofactors of f, and determinant of f. In order to account for interactions between these invariants, we also add terms that involve their sums. But now, how to guarantee polyconvexity when the strain energy is in the form of composition of functions? To understand this, consider a simpler function f, which is obtained by applying a function g on h. If h is convex, g is convex and non-decreasing, then f is guaranteed to be convex. In our case, we need these invariants to be convex functions of their arguments, and the components of strain energy to be convex and non-decreasing. Luckily, the first part of this is already proven to be true. But how to guarantee the second part? Spoiler alert, that is where we use neural ODEs. But before we move on, another point that I want to mention is that the value of the strain energy itself is not very important for us. What is really important is the value of its derivatives, because those give us the tensors of stress and elastic moduli. This function can be differentiated using chain rule. But now, how do those requirements on the components of strain energy translate to their derivatives? Well, if a function of a single variable is convex, its derivative is monotonic. And if it is non-decreasing, its derivative is non-negative. And vice versa. So now the problem of obtaining a polyconvex strain energy function boils down to guaranteeing that these derivatives are monotonic and non-negative. Which brings me to the next part of my talk, neural ODEs. A neural ODE is a computational framework. It takes an input and produces an output. At the core of the neural ODE lies an ordinary differential equation, the right-hand side of which is given by a neural network. The inputs of the neural ODE constitute the initial conditions of this ODE, and the solutions of the ODE at some predetermined time are the outputs. For any given value of the input, the ODE can be integrated up to the final time to obtain the output. But ODEs have an interesting property. Their solution trajectories never intersect. This means the input-output map of the neural ODE is always monotonic. We can also tweak the neural network and inputs of the neural ODE such that the outputs are always non-negative. Which means that if we approximate these derivatives with neural ODEs, we guarantee polyconvexity of strain energy. And with that, we go to results. First, we generate some synthetic data with a widely used analytical material model, GOH. Here is how the data looks like when we plot the contours of strain energy against components of Lagrangian strain. We use some of this data to train the neural ODE and regenerate the same figure with the predictions of the neural ODE. First, it is worth noting that only about 1/4 of this data is used in training, but the neural ODE still recreates the entire domain almost perfectly. This is one of the advantages of using an invariant-based approach. But aside from that, contour lines of strain energy show that the strain energy is indeed convex, as promised. But this is unsurprising because the data itself is also convex in this case. Interesting things start to happen when we train the neural ODE with non-convex data. For this, we repeat the same procedure with a func-type material model that is not convex. Can you guess what happens when we train the neural ODE with this? The neural ODE is simply unable to learn this kind of material response because its building blocks prevent it from violating polyconvexity. It still tries to match the training data as well as it can, but within the bounds of polyconvexity. And that's a good thing, because this training data is physically unrealistic in the first place. Next, we train the neural ODE with stress-stretch data obtained from biaxial experiment on porcine skin. These points are colored according to the error of the neural ODE at each point after training. Here is how this plot looks like if we bring the stretch in the other direction into the picture. Three of these 5 loading paths are used in training, while the other 2 are saved for validation. We perform the same procedure for 4 widely used closed-form models, which are GOH, Mooney-Rivlin, SGO, and Fang. The neural ODE has by far the lowest training errors, as well as the lowest validation errors. In another numerical experiment, we trained the models with the first 80% of each loading curve and test with the remaining 20%. The neural ODE has the lowest validation error in 3 out of 5 cases, as well as having the lowest average error. We implement the neural ODE-based material model in the U anisohyper subroutine of Abacus to enable FE simulations. To test the viability of the model, we start by performing some simple simulations on a small square patch of skin, such as uniaxial loading, shearing, torsion, and tissue expansion. The results of these simulations indicate that the neural ODE-based material model is working without problems in Abacus. We then move on to realistic simulations of human tissue. We perform a virtual surgery in the scalp of an actual cancer patient using a realistic patient-specific model. The simulation predicts locations of stress concentration during various stages of surgery, which enables better planning of the surgery. To conclude my talk, we develop data-driven material models where polyconvexity is satisfied a priori. The model outperforms many widely used closed-form models when trained with experimental data. We implement the material model in a widely used commercial FE package to make it available for immediate use in application. All of our data, source code, and FE models are openly available in a public repo. Thank you for listening to my presentation.